Most people look at a tangled mess of string and see chaos, but mathematicians see a geometric DNA. This is the world of knot theory, where we ask, is this tangle actually just a simple loop in disguise? Think of a knot not as a string, but as the boundary of a magical, invisible surface. We call this the Seyfert surface. The holes in this surface tell us exactly how complex the knot is. A knot is simply a closed curve embedded in 3D space. It has no ends, it's a loop that might be twisted, but never cut. The simplest knot is the unknot, just a circle. Next is the trefoil, the simplest non-trivial knot. If I give you this Gordian mess, how do you prove it's just a circle? You can't just look at it. You need invariance. Two knots are equal if you can deform one into the other without cutting or passing through itself. This continuous motion is called an isotopy. To track these changes, we use Reidemeister moves. Move 1, the twist. You can add or remove a loop without changing the knot's identity. Move 2, the poke. One strand can slide over or under another entirely. Move 3, the slide. A strand can slide across a crossing. These 3 moves are the only ways a knot can change its appearance without breaking. But there's a catch. Crossing number isn't a perfect invariant. A knot can look complex but be simple. We need something deeper, the genus. To find the genus, we look at the surface the knot bounds. For a sphere, there are no holes, so the genus is 0. A torus or donut shape has 1 hole. Its genus is 1. The genus is simply the number of handles or holes. But knots aren't closed surfaces like donuts. They are boundaries of surfaces. Imagine a disk. Its boundary is a circle. The disk has genus 0. Every knot is the boundary of an orientable surface. This is the Seyfert surface. The genus of the knot is the minimum genus of any surface it can bound. How do we build this? Step 1. Assign an orientation, a direction to the knot. At every crossing, we cut and reconnect following the arrows. This leaves us with a set of disjoint Seyfert circles. Now, we place these circles at different heights and connect them where the crossings used to be with twisted bands. To calculate the genus, we use the Euler characteristic. Chi equals V minus E plus F vertices minus edges plus faces. For a triangulated torus, we have 4 vertices, 12 edges, and 8 faces. 4 minus 12 plus 8 equals 0. So for a torus, chi equals 0. For a surface with B boundaries, the formula is chi equals 2 minus 2g minus b, since a knot is just one boundary. B equals 1. Using Seyfert's construction, we find that chi also equals circles minus crossings. Chi equals s minus c. Set them equal, and we get the holy grail of knot genus. G equals 1 minus s plus c over 2. Take twist knots. For these, the number of circles is always 1 less than the crossings, s equals c minus 1. Plug that into our formula, and we find that every twist knot has a genus of 1. No matter how many times you twist it, its complexity core remains the same. This tells us twist knots are prime, the atoms of the knot world. They can't be broken down further. By looking at the skin of a knot, we've uncovered its soul. If you now see the surface beneath the tangle, you're already ahead of 99% of students. Subscribe for more mathematical deep dives, and I'll see you in the next dimension.